So welcome to today's Autonomy Talk. Today is my pleasure to introduce you to Riccardo Bonalli. Riccardo is a postdoctoral scholar at the Stanford University's Autonomous Systems Lab. In particular, so Riccardo got his master's in mathematical engineering from Politecnico of Milan, and then his PhD on from the Sorbonne University, working with the ONERA, so the French Aerospace Lab. For his PhD, he won his best PhD award, and as I said, he then left France, sadly, to go to California. On a personal note, Riccardo is really a connoisseur of Italian cuisine. In fact, I met him just 1 hour after I landed in California for the first time, and he brought me to this pizzeria in Palo Alto, which was really good. And since then, basically showcased us all the places where you can have good Italian meals in California. So that's really another skill he has. Today, Riccardo will talk about composable geometric motion policies using multitask pullback bundle dynamical systems. And I'll leave you the stage, Riccardo. See you later.
Thank you very much, Joelle, for the very nice introduction. So this work is a joint work with Andrew Byler and Marco Pavone from ASL. So before getting started, I would like to introduce you to my research a little bit, trying to make you understand why I got interested by this kind of topic. So my general concern is, let's say, devising algorithm for a robust optimal control of dynamical system. Application span from aerospace, aerospace robotics, and robotics in general. Mathematically, those kind of problems have a very clear formulation. So we try to minimize, some kind of cost in some given space of control, because real application are affected by uncertainty. So costs might be expressed in expectation in some kind of probability space. Recently I also investigated costs that are more involved, such as like risk kind of cost. We are subject to some dynamics, and because of uncertainty, we would like to consider, the very general case of a stochastic process driven by, possibly Stratonovich integral, and we are given initial fine condition, and we would like to satisfy given state and control constraints. Importantly, the space of the variable that describe my system, we don't require the space to be Euclidean. We can have some kind of structure such as a manifold. And so towards the goal of trying to provide an algorithm that works in real time, I developed several methods, two in particular that I wanted to point out. So considering nonlinear deterministic system, I could achieve real-time computation by leveraging basically necessary condition of optimality in the Banach space of the optimal control problem, known as Pontryagin maximum principle, to solve those 2-point boundary value problem. And when convergence is achieved, those algorithms are very fast. In order to deal with uncertainty, I try to extend this formalism by considering a kind of very old approach, actually, sequential complex programming, that, however, never been used in this kind of context. And the idea is to, iteratively linearize and solving instead a sequence of convex stochastic problems. We can provide theoretical guarantees by leveraging control theory and Ito calculus. And why I wanted to put attention on this, because those methods, for instance, they share a common drawback. which is the initialization. Specifically for a system with a very high number of degrees of freedoms, the initialization matter a lot. And so this brings me to today's topic, which is how do we provide motion policies for generally complex dynamical systems in real time. And an example of why this is useful can be understood by analyzing this nice picture, whereby we have 7 joint manipulators, and we would like to move a ball constrained to lie on the surface of a sphere by avoiding any collision. And the approach I'm gonna present leverage Lagrangian mechanics and some tool in differential geometry, introducing a new class of system that we called Pullback Bundle Dynamical Systems. So in order to better understand what is the problem we need to deal with, let me start with a very simple example. So in general, policy synthesis it's very difficult. Let's say, for example, a very standard problem, which is like planning, basically. Here I consider a 2 joint manipulator. Degrees of freedom are θ1 and θ2. Those variables belong to circle times circle. This is what we call the configuration manifold, and from now on I will denote this space by M. Is a general manifold a priori. And so the goal would be to grab, let's say, the blue mag here by avoiding any collision with the other 2 red mags and the table that are here considered as offsets, right? And so the problem would be to design a curve sigma in the configuration manifold such that when we compute the position of the end effector, which is a function of this curve, of course, we know that for every time the end effector will be outside any obstacle, and for hopefully for a given final time, the position of the end effector will be at the goal. And so everyone knows that already in a very let's say basic context, let's say like this one, only 2-dimensional system, the problem is already pretty hard to solve. So imagine doing that for more many degrees of freedom and trying to achieve real-time computation. And so the alternative that we propose consists of, rather than planning on the original configuration manifold, we plan or we synthesize a policy first on task spaces. Okay, so the idea is the following: we define mappings Fi that go from M to Ni. Ni will be the task space, the ith task space, that in this case I will take to be the non-negative real numbers. And so those functions basically in this context represent the distance for a given configuration of the robot of the end effector with respect to all the 3 obstacles and the goal. And so this way of solving the problem develops in 2 main steps. So the first step consists of designing curve in the space of task, denoted here by di, and those curves should be such that, for basically the 1, the 2, the 3 that represent the distance with respect to the 3 obstacles, those distances are strictly positive, so there won't be any collision in time. And the 4th distance, which is the distance with respect to the goal, at a given final time t, this distance is 0. So this step, it's supposed to be easy because those task spaces are a priori independent, and are of lower dimension. So the problem is technically easier to solve here. So only at the second time, we try to derive a curve sigma on the original configuration manifold, such that when we map this sigma curve through those task mapping Fi, those curve resembles every distance curve that we compute previously. So that's the main idea. So this way of proceeding is not new, of course. It's been studied from a very long time, and along this line, two main works are of interest for us. So the first class of works consider artificial potential functions, and the idea is that we model collision avoidance and go region attraction through potentials. So repulsive potential for collision avoidance and attractive potential for go region attraction. And so this way of thinking makes things pretty easy, in the sense that computationally the method is pretty efficient. The problem is that the presence of many potential might provide, the existence of many local minima. More recent work, which is RMP flow, try to handle and fix the presence of local minima by removing potential and replace them via Riemannian metrics that basically on each policy deform the space so that they basically make the region in which the obstacle lies inaccessible. This method, it's very effective, but we discovered that at the end it's geometrically inconsistent in the following sense. If we represent the system with a different local chart, different coordinates, the answer provided by this algorithm might be different. So which is something that we would like to avoid. And additionally, this kind of method, it's kind of difficult to tune correctly. And so having said that, our objective, it consists of providing a method which is locally minima free, computationally efficient, geometrically consistent, and definitely easy to use. The way we proceed follow the two main steps I mentioned in the example, right? So specifically, first we design trajectories on the space of task. Task, I remind you, could be something like, avoid obstacle A or reach region B, etc. And so we ask that those curves are solution to a new class of mechanical systems that we introduced that we call Pullback Bundle Dynamical Systems. At the second step, we try to finally recover a trajectory in the configuration manifold that achieves all the previous, all the tasks basically, by appropriately projecting the acceleration of the solution coming from the previous PBDS. So the intuition with which we developed this method came from actually Lagrangian geometric mechanics and some bundle theory in differential geometry. So in order to provide you with some of the interesting details of this method, I first need to recall some tools of differential geometry and Lagrangian mechanics. So I try here to avoid very precise definition. It's not the objective. I will try to give you an overview of what those tools actually mean. And so let's consider M be a configuration manifold. We have I task manifolds Ni, and we are given I task mappings Fi from M to Ni, okay? And so in classical Lagrangian mechanics, of course, the first thing we would like to deal with are velocities and accelerations. So when we do mechanics on manifold, those concepts are correctly captured by the notion of tangent bundles. So tangent bundles are spaces that are basically given by disjoint union. So for every point in the manifold P that should be understood as a position, we take basically, we associate this position with a given velocity taken from this vector space, which is the tangent space of the manifold M at P. And so velocities here in geometry are nothing else than a tuple of position and, if you want, a Euclidean velocity. And the same thing is iterated for accelerations. So we, instead of taking the tangent bundle of M, we take the tangent bundle of the tangent bundle of M, whereby basically we have what we call based point here, are a given position and a given velocity in Tm. And we associated to this tuple a Euclidean acceleration, so that acceleration, geometric acceleration, are actually tuple of position velocity and Euclidean acceleration. Of course, when we do mechanics, we need to deal with calculus. So the correct way of differentiate function between manifolds is by using differentials. So differential of a general smooth mapping, and let's take for instance here the Fi task mapping. It's another mapping between tangent bundles, so between velocities, if you want, such that for a tuple PV, we associate the following tuple here. The base point is given by the image of the function, and the second coordinates is basically the output of, the Jacobian basically of this mapping computed at the velocity. And this is also called as geometric Jacobian. Of course, we cannot do mechanics without the notion of dynamics. And in differential geometry, dynamics are correctly captured by the notion of vector field or sections of the tangent bundle are nothing as a mapping from a manifold to its tangent bundle, such that the vector field evaluated at a point P, so this is just a notation, standard notation in differential geometry, belongs to the tangent space of M at point P. I will use this notation for the space of vector fields. So we're almost done. We just need two more definitions that will be actually the most important for us. So I need to introduce the definition of Riemannian metric. The idea is that we don't really see the importance in classical Euclidean mechanics of a scalar product, actually, but it's used constantly when we do computation. And the idea is that we need to extend this notion also when we treat mechanics, but on manifolds. And this notion of scalar product is correctly introduced by Riemannian metric, that are basically functions such that when evaluated at P, this mapping here is nothing else than a scalar product of on the tangent space TPM. And so the importance of introducing Riemannian metric is the following. They provide us with a correct notion of geometric acceleration. Let me be clear. Specifically, we can prove that to any Riemannian metric we can associate a unique operator, which is called linear conjecture or the associated Levi-Civita connection, which is nothing else than an operator denoted by nabla here, that takes two inputs, specifically two vector fields, x and y. The output will be a vector field as well. And without entering in the detail of the definition, the idea behind is that this operator allows us to provide a notion of derivative of vector field y along the direction given by x at each point. And when instead of x and y, we take, for example, the derivative of a curve on a manifold, so a kind of a special vector fields, if you want. These operators provide the current notion of acceleration when we consider a manifold. So basically the term A in the Newtonian equation ma equal to f when we consider manifold. That's it. So as I mentioned previously, so before getting into Lagrangian mechanics to explain how we derive our new mechanical system, I need to introduce further definition, because as I mentioned before, we would like to plan in the task spaces, but at the end obtaining trajectory that lie on the original configuration manifold. So this gives you the the feeling that we must kind of deal with velocities on the task spaces, but with base point, so position, for instance, in the configuration manifold. So in order to introduce this definition correctly, we leverage the notion of pullback operation in differential geometry. So let me be clear on that. Although all the previous definition adapt in the following sense. Instead of considering tangent bundles, so velocities and accelerations, classical one, we consider pullback bundles. So pullback velocity and pullback acceleration, or if you prefer, task velocity and task acceleration. The construction is the same. We take a disjoint union whose base point is P, but instead of taking velocity in the configuration manifold, if you want, we take velocity in the space of tasks. And the same thing is iterated for accelerations as previous. In the same way, we adapt the notion of differential by using pullback differential, basically, which is nothing else than the previous operation, whereby instead of taking as a first coordinate the image of the previous mapping, we just take the same base point. Similarly, vector fields are replaced by pullback vector fields, whereby basically the mapping, this mapping goes from M to the tangent, sorry, the pullback bundles instead of the tangent bundle. Metric, Riemannian metric become pullback metrics, which basically for a base point position P in the configuration manifold, we take a scalar product between velocities in the task space. And this will allow us to introduce a correct notion of now task geometric acceleration, whereby basically we use a pullback connection instead of linear connection. And the first input will be always a vector field in the original configuration manifold, but the second input, y, will be a pullback vector field. So right now we have all the tools we need to introduce the evolutionary equation will be used for policy. So how do we do? So because I told you our intuition was driven by the classical Lagrangian mechanics framework, I would like to first recall the step with which we provide axiom of motions in geometric Lagrangian mechanics. There are several in the literature. Here I will stick to, let's say, the easiest one, knowing that the vast majority of them we can prove to be the same, D'Alembert principle or minimization of action of Hamiltonian action, etc. So we proceed in 3 steps. So the first one is defining a metric. By the way, let me let me mention that here there will be no presence of task manifolds, and we just consider the standard configuration manifold. So we define a metric G on the configuration manifold. This metric its norm will represent some kind of kinetic energy a priori, okay? This is a particular representation of Lagrangian mechanics. We also choose forces, okay? So the notion of forces must be adapted. Forces are mapping from tangent bundles, basically. In the literature, you will find a slightly different definition of force. Here I use an abuser notation because I don't want to charge too much definition for clarity. But everything works out more or less the same. So once we define those quantities, the second step consists of providing a geometric acceleration. The geometric acceleration that basically it's imposed on the system. And this is given, as I mentioned before, by associating the selected metric with its unique Levi-Civita linear connection that I represent here by nabla G. So this is, a connection that give a current notion of acceleration on a map. And with these tools now, you are able to introduce an axiom of motion, if you want, which is the following. Given any initial condition P0 position and V0 velocity in Tn for our system, we force the trajectory of our system, feasible trajectory, to satisfy the following ODE, if you want, on manifold, whereby basically we have a curve here, which is an acceleration, basically, that's the idea, equal to generalized forces, okay? So to give you more insight on what's happening here, let's write down this equation in local charts. That is, this equation is an equation between specific operators in differential geometry. And when we evaluate those operators locally in local charts, local coordinates that represent the manifold, we end up obtaining something like that, okay? Whereby you recognize for every coordinate scale, every dimension, we recognize the classical, if you want, Newtonian acceleration, which is basically weighted by these other terms and depend on the velocity. These quantities are known as Christoffel symbols and are uniquely given by the Levi-Civita connections, okay? Cool, so with this framework in mind, we now ask ourselves, okay, how can we leverage this insight, this information to build axiom of motions on the space of task, which basically provides us with trajectory in the original configuration manifold. And so we proceed in the following way. So as previously we defined, so now everything in the space of tasks. So we define for every task I, from now on I will be fixing a task I. We define a metric GI and forces. And from the metric we extract its Levi-Civita connection. So the way we build, so those quantities are supposed to be easy to provide to achieve the task, because the task it's supposed to be a space of low dimension with low interaction. And I will show you later on a practical example how we can provide those elements. But for now, believe me, we provide for every task those elements. And so the next step consists of basically, for now, we have defined everything on velocities on the task, if you want. We now to project everything back, defining additional operators in order to retrieve curves in the original configuration manifold. How do we do it? We leverage the definition, the pullback definition that I introduced previously. We associate this linear connection with a pullback connection denoted in this way. Those Christoffel symbols are given by those equations here. And similarly, we can define pullback forces, okay? And so now you understand that this operator acts on the space of task velocities, whereby the first coordinate is a position in the configuration manifold, but the velocity part now is given by velocities on the task manifold. And with these tools, we can define our own action of motion that we know we call Pullback Bundle Dynamical System here below, which is nothing else than basically an evolutionary equation on a manifold. Similar to the previous one, we have a pullback connection equal to pullback forces. And we denote basically for every initial condition in the tangent bundle of the configuration manifold, its solution by alpha I that depends on PV. Those are curves, okay? What is the representation behind? The idea is the following: for every task, no matter where we are in the space, in which point PV, we can compute for every at this position, at this initial condition, sorry, a curve alpha I, such that if we let this curve evolve, it will achieve the task. Think about, for example, the task, the go region of attraction. So for every initial condition in TP, for every point in the tangent bundle of the configuration manifold, we will be provided with a curve that achieves that goal. So in other words, we found basically a way to kind of, synthesize policies in the space of velocity of tasks, obtaining curve in the configuration manifold. So now the next step, the second and last step, is trying to gather all those curves in the configuration manifold that singularly achieve the task into one unique curve, sigma, in the configuration manifold that is supposed to achieve all the tasks. Several solutions are available, of course, I won't deny that. We choose a specific one which is more intuitive from a control point of view, which is the following. We look for curve sigmas in the configuration manifold, whose task acceleration is kind of the closest to the task accelerations of all the previous AIs at every point. That's the idea. Specifically, we proceed in 3 steps. So the idea is that we are dealing with kind of different quantities and we would like to compare them. So we need to find out an operation that lift and project all those quantities to the same space. And we quickly understood that this space is the space of task acceleration. So remember, this is the pullback tangent space, so point in the configuration manifold, velocity in the task space, and we are taking acceleration, so acceleration in this pullback bundle here. And so the idea is that we have an operator that to which will be given the acceleration of this curve sigma, and we'll map it to a task acceleration. And the second operator acts on this curve alpha I compute previously at a given point PV as an initial condition. Those operators are importantly defined through these additional operators pi VB, which denotes basically the projection onto what we call the vertical bundle. Let me explain quickly what that means. Basically, element in this space can be written as kind of vectors, if you want, along 2 sets of coordinates. The one that depends on the base point and the other set that depends on the task velocity. And what we are doing here is that we're just selecting the second group of coordinates and depending on the task velocity here. Why I wanted to mention this a priori useless minor detail, okay? Because we discovered that this is one of the main, there are other, but this is the one of the main flow in the RMP flow approach, whereby they try to achieve a similar construction, but projecting onto basically horizontal bundle, which is given by the first group of coordinates, if you know. Consistent operator, well defined. The horizontal projection is not well defined. Gele, can you hear me?
Yeah, I lost you for like 2 seconds. I don't know if that's only me or...
Yeah, no, I saw there's an issue, I guess. But so I can repeat the last part.
Yeah.
You tell me if you don't understand, because yeah. So the idea is that in the RMP flows, they select the first part, which is not correctly defined, and this is one of the main flaw of this approach RMP that makes him basically geometrically not correct. Steps, okay, let's provide the dynamics, the final dynamic policies, try to make this cube achieve all the tasks. And we do it through a minimization problem. Because we have a minimization problem, we need to introduce appropriate cost. And because we deal with acceleration, the cost we'll be introducing are metrics in on the manifold for every policy I on the tangent bundle of Ni. So specifically, this metric is a scalar product over the acceleration. So for every base point PV, this metric will be given an acceleration. Okay. Because of course we are considering task accelerations, we need to kind of pull back this metric. It's a kind of non-operation, and at this point we are able to provide the dynamics F that the curve sigma is supposed to follow, which is nothing else than a vector field being the dynamics whose image is the space of configuration manifold acceleration, TTM. More precisely, we are giving a velocity, so PV, and we are selecting the acceleration A here, that is the minimum of this scalar expression. So here, what we're doing, we are summing up basically all the difference, if you want, and those are costs, remember, of the acceleration projected on the task acceleration space of the sought acceleration A against basically the acceleration in the task space given by each pullback bundle dynamical system, each policy that we compute previously. The third step is then to integrate this system, right? So we define a final, if you want, axiom of motion, which is the following. The trajectory sigma, the desired strategy that we want to achieve, is the solution to the following differential equation of manifolds. Its second time derivative, which is an acceleration on the original configuration manifold, equals this acceleration here. So to give you an insight, locally, so when we basically take this equality, we develop this problem. This problem is correctly well posed because metrics are definitely positive, so everything is kind locally at least convex. So we can solve this problem through basically derivatives. We can solve it analytically, we can impose the equality, and we find out that locally, this equation can be written in this way, whereby basically you see, the sum of some components due to every pullback bundle dynamical system weighted by this pseudo-inverse operation here, okay, that considers also the cost. This alpha I term is the one that you see below and is basically part of the Pullback Bundle Dynamical System dynamics that we developed before. And numerically, it's pretty easy to compute. We can do it instantaneously. So far, so good, but I guess I agree with you that this looks like pretty complex, right? And so we ask ourselves, what are the benefits? There are several. Let me list you the main ones. First of all, geometric well-posedness. The idea is that we want this method, which is given, quantities over a manifold. We want this to be consistent, no matter what representation of local chart, basically, we selected to represent our system. So in these two pictures here, we try to solve the following problem. We are on a sphere, we are at a given initial point, we want to reach another point by using this formalism. So here on the left, you see the solution given by our methods, considering basically the resolution of the previous equation, sigma double dot equal f sigma dot, by evaluating that equation over 3 different representations. And what we get is exactly the same answer for any representation, which is what we want. When we try to solve this problem by the original RMP flow, this is what we get. So different charts give you totally different answers, okay? And so the interesting thing is that we could manage this inconsistency, which is pretty important. So second, the idea is that, okay, we are given solutions to a dynamical system, and we would like them to be, nicely behaving, in the sense that at some point we have convergence to some desired objective. So the idea is that we, in mimicking the standard framework, whereby forces are the generalization of a gradients of some potential functions and some given dissipative forces, we can prove that the following function here is a Lyapunov function for the system. And therefore, by invoking LaSalle principle, we can prove that we converge to basically the minima of the involved potentials, that actually it will be a function of the potential and the previous cost that I mentioned before, which is totally consistent with the framework we developed. Something that I want to point out is the following. Similarly to what RMP did, if we model collision avoidance, not by potentials, but by stretching the space over policies through Riemannian metrics, which is what the framework make you capable of. This result will tell you that you will converge to the unique minimum of the unique potential existing, which is basically the one used for the attractor policy. Finally, we can prove that we are kind of like computationally efficient, and the whole method is pretty easy to put in practice. So for that, I will like to present you a very simple example to show you how it's kind of easy to set things up, okay? So since I mentioned too many times, I guess now it's the time to explain you how do we plan, if you want, on the unitary sphere. So the idea, the objective is, given an initial position, we would like to reach another point on the sphere by avoiding any possible obstacle that is placed on the surface of the sphere, okay? So here the configuration manifold is the unitary sphere by definition. And we are gonna define 3 kind of tasks. And what you're gonna see is that the design of those, it's pretty general. So this framework apply for no matter what kind of planning that you want to do on any configuration manifold a priori, okay? So the first kind of task is goal attraction. And so the idea is the following. The task mapping that we choose is the following. For at every position on the sphere, we associate the distance between this point and the final goal, okay? And the idea is that by imposing a standard potential then on the task manifold N1, which is just R, a standard attractive potential, so we can basically, we force the system to reach the goal at a point actually Q1 equal to 0, okay? So you see that because we are just defining stuff on R, those are pretty simple, no matter what is the shape of the manifold M, actually. So the second kind of, by the way, there are no dissipative forces, and because we need to enforce some metrics to correctly define our, capital F dynamics, here we'll be using a standard stretching of the space. So we just take metrics to be the product of two real numbers, basically, the simplest one. The second kind of task are collision avoidance, and I guess this is the most interesting one to discuss because it shows you the very nice properties of this method. So as task mapping, we select the distance from an object, and so of course we need to require the boundary of obstacle to have some kind of regularity so that this mapping is well defined and smooth enough. Of course, for object more standard geometric form like spheres or some polygons, we also have like analytical formulation of this stuff. And the idea is that we, as mentioned before, collision avoidance, there's no presence of forces, so no potential, no dissipative forces, we just define metrics. The Riemannian one on the task and the cost one. The Riemannian one is simple. So by the way, metrics here, we need to define them on R. So it's pretty simple, no matter what is the shape a priori, technically, of the obstacle and of the manifold, because this is the difficulty, if you want, here is only dealt by F2. And so the Riemannian metric, we choose something that basically explodes as soon as we reach basically the objective. So as soon as we go close, if you want, to 0, which is the region in which the obstacle is placed, we stretch the space, okay? And so for the cost metric, we choose this one. So the idea is the following. This task should matter only if we are very close to the obstacle and we are going towards the obstacle. If we are going away from the obstacle, there's no need to consider it. And the idea is that here clearly we see the importance of defining cost metric that depends on the velocity as well. And okay, by the way, I mentioned before that we needed a real metric, so a definite positive quantity. This quantity is only semi-definite positive, but we can easily prove that the previous dynamics is always still correctly defined as smooth. The final task is something that we need to make the convergence analysis rigorous. So you know that if you want convergence, you need to remove energy from the system. That's a pretty standard mechanical principle. And so we impose a task of energy dissipation, just one that deal with all the energy of the system, by selecting basically the identity as task mapping. So the manifold N3 is just M, and there are no potential forces. Only dissipative one, the very standard one. Here we can also select basically a coefficient to module if you want the velocity, but And so what about the metric? We don't need specific metric here to stretch the space. It's not required, but we need to put some consistent metric. So because we are on the sphere, as a Riemannian metric, we define on the sphere, we define basically the round metric. And for the cost metric, we can provide an induced metric from the round metric, basically. And so if we put all this together and we compute the dynamics F, we integrate the system numerically, we obtain something like that. So here we are basically shooting particles on the sphere with different initial conditions and let them evolve just through the dynamics F. And this is done basically, I would say in real time, because we are just integrating a dynamical system, an ODE basically. Cool, so I guess I'll end here, and I just want to mention some interesting extension of this approach. So what we define here, it's kind of pretty new, so there are a lot of things that we can improve, of course. Three are kind of interesting, three extensions. So the first one is like extending the formalism by considering Finster geometries instead of Riemannian geometries. And the idea is that Finster geometry allow you to consider situations that account for asymmetries. An interesting one, for example, is the following. Consider you want to go from A to B and you want to avoid an obstacle that is actually in between those 2 points. So the present formalism gives you basically a strategy of this kind, and we go towards the obstacle. As soon as we enter into an unsafe region, we just, push on, for example, the right, we avoid the obstacle and we get back to the straight line towards the goal. But consider another situation whereby maybe for an autonomous vehicle, you would like, for security reason, maybe to decelerate as soon as you go towards the obstacle, turn right, for example, and as soon you are basically away from the obstacle, you start to accelerating again. So there's this notion of asymmetry, of course. Second of all, we would like to encode the tasks such as trajectory tracking. That's something we can't really deal with right now. And of course, very importantly, I guess any of you have noticed that we can't really consider dynamics in the sense, original dynamical constraint, if you want, of the system that we can force. Okay. So I thanks my collaborators, Andrew Byler and Marco Pavone. By the way, let me mention that we're gonna submit this contribution to NICAR soon, and we are developing basically hardware experiment and numerical experiment of a robotic arm. And thank you for your attention, and I will be glad to take any of your questions.
Thank you very much, Riccardo, for the cool talk. Are there any questions from the audience?
Can I start with a maybe technical question?
Yes, go ahead.
So I had two questions regarding the definition of pullback tangent bundle. Can you maybe go back to the slide?
Sure. There we are.
So here there's no regularity assumption on F, right? This is well defined. Like all of this is well defined for any Fi.
Sure.
Right?
So yeah.
Because you're just pushing your point P to Fi of P.
Yeah, that's the idea, right? So yeah, let me mention that I guess I mentioned it, but here I'm just considering smooth functions, of course. So at least let's say C1, but a priori, as soon as just the definition of the pullback is well defined, no matter for which function. Of course, then the regularity of the pullback as a manifold itself will depend on the regularity of Fi as well, of course.
So that means the pullback tangent bundle wouldn't be a manifold if F is not regular enough.
Correct.
It would still be?
The correct claim will be F star T and I is a manifold, is a K manifold if Fi is CK.
Okay.
That's
okay. And another question, I think a few slides later, you come up with an evolutionary principle to essentially mimic the differential equation you have in Lagrangian mechanics. I was just wondering, do you have existence for free of a solution, or did you have to kind of prove that this exists, or is that an assumption?
Yeah,
because I assume this is well defined in like classical Lagrangian mechanics. That, I mean, I'm sure people studied that. I was just wondering if this holds true even in this artificial mechanics.
Correct. That's very very interesting and good question. You're right. So there's no a priori guarantees of existence, uniqueness, or regularity with respect to the data concerning the solution of the systems. But what maybe I haven't mentioned for time is the fact that basically you see here the second vector field we are giving to this operator, pullback connection, is precisely defined in this way. And so if you take those cubes and you plug them in, you evaluate in local coordinates this equation. So this is just a well-defined second order dynamical equation, which, however, whose technically derivative, you have a derivative of a composition of a Jacobian and alpha, if you want, alpha dot. And so you, by you know, taking the derivative of this product, you will have, you know, the important term is like Jacobian times alpha double dot. And you would like to end up with an ODE, so you would like to, you know, put the inverse of the Jacobian on the other side, or a pseudo inverse, right? So as you mentioned, in order to do that, to make it correctly rigorous, we need to ask that for every task, the task mapping has full rank, or in other words, is a submersion action, okay? That's the requirement we ask. So if you ask that, we can prove everything as in the classical case, existence, uniqueness, and regularity with respect to the data.
And you even get unique, existence for all times. Yes. That means time going up to infinity.
Yeah. So okay, here for just clarity, I put 0 plus infinity, but of course you have local existence as the standard case. And under additional assumption on the local shape of those mappings, for example, you know, linear growth or boundedness, basically, you can prove existence for all time by gluing basically charts all together. That's the standard way you proceed on manifolds.
Okay, thanks.
Are there any other questions?
I have a question, if I can ask it, Joel.
Sure, go ahead.
I'm Severi Bolognani from Automatic Control Lab, and we've also played a bit with dynamical systems on manifolds, but in our case, the tricky part was the presence of constraints on the manifold. So we had projected dynamical systems on the manifolds. And in order to make our projections, everything work, we needed some regularity on the metric, like being continuous and locally bounded Lipschitz for some of the results. But I see that in your, at least in the examples, I think slide 13, you don't need that. Is that correct? Or do you need to do some extra technical tricks to make it work? Or is it as simple as it is in the slide? Like you don't need the metric to be continuous locally Lipschitz or Lipschitz in this case?
Yeah. So no, actually, what you see up to basically, there's something I haven't defined, but the stuff I've defined here is pretty much almost everything we need, and it's defined exactly in that way. So in order to better understand your question, you said that you consider the, constraints on the manifold, right? So
on the manifold, so exactly. So we need to project on the tangent cone to those constraints, right. And that requires properties of the metric.
Yeah, so that's a kind of different approach, because here what we do is that, in other words, we are not defining the metric at a point 0, right? Even though 0 technically belongs to the manifold, right? We are just preventing, if you want, the system from physically getting there. That's
right.
the way we do it, right? And so, and the key step is basically defining stuff on this on the task manifold, which is very simple. It's just R, and let all the difficult parts be dealt by F2. That's the idea, and this can be correctly given if you adopt this pullback idea behind. In something that I would like to add is that, like in your case, it's kind of, you know, forcing like hard enforcement of constraint by those, right? And here it's different. We are not like, you know, enforcing like hard constraints. We are just kind of modifying the space itself so that there is 0 probability that the point will be at 0. That's more or less the idea.
Does it work fine when you discretize these trajectories? Because at least, I mean, vaguely speaking, sometimes barrier methods tend to be a bit tricky when you do discrete time integration of these. Is it something you observed as well, or not?
So I guess it works fine. Yeah, I mean, Andrew might have more details about that, but Andrew, the other collaborator on this project. But yeah, no, from what I remember like there was no particular issue in geometry, in numerical integration. What really bothers us was at the very beginning, we were trying to understand what before developing this framework, what people have done with the RMP stuff, RMP flow. I don't know if you were aware before of this work.
No, I wasn't.
Yeah, so they we saw basically a bunch of very weird behavior happening, and we suddenly understood that that came from, of course, a bad tuning of the method, because their method, basically the metric here, the Riemannian metric, is also it does depend on the velocity as well, and so it becomes very complex to design tasks in their case. And moreover, they had those geometric inconsistencies. So they were forgetting basically part of the metric and projecting onto basically a tangent bundle on components that are basically that on different charts change basically basis. And so, yeah, at the very beginning, what we saw, it was that their method was not working really correctly, you know? And so we basically developed this method to fix what they were providing, because beside that, their method is very efficient in considering, you know, metrics in order to avoid collision avoidance.
Just to add a little bit, I think you were wondering about this omega weighting metric that we use. And I'll just add that this is what we use numerically in practice, but of course, theoretically, you may want to consider some smooth approximation of this.
Yep. Yeah. That's very interesting. Thanks a lot.
Sure. Thank you.
So are there any other questions? Right, if not, I think we can thank you, Riccardo. People have your coordinates if they want to reach out for more specific questions. Thank you very much, and good luck for your next steps.
Okay, thank you very much. Thank you very much for inviting me, Joele, and thank you very much all for having seen that. Thank you. Bye.
Bye-bye.